and Rodolfo Russo, and in particular one with Alessandro and Rodolfo appeared a couple of days ago on the archive, and also here and there throughout the talk I will skip some details in the presentation, especially concerning the gravitational eikonal exponentiation, for which instead I refer you to a review that we wrote together with Paolo Di Vecchia, who is in the audience, Rodolfo Russo, and Gabriele Veneziano. So here is a schematic outline of the talk. Well, I will start with a few words of introduction and motivations, just to set the stage for the ensuing discussion. Then I will review essentially the current understanding of this subleading waveform I was mentioning. In fact, I will actually start by analyzing in somewhat greater detail a well-known case study, which is not directly related to the waveform, has to do with how we extract information about the deflection angle, or the so-called impulse, for the elastic case. This is a well-known and well-studied observable that, however, will be very instructive for us and will allow us to generalize some considerations to the case of interest today, which is instead the one in which we also have gravitons in the final state. We are really doing dealing with the waveform itself. Then after this, we will use this sort of improved understanding about the waveform to obtain some explicit results, as I was mentioning, concerning the soft limits and the post-Newtonian limits of the waveform. And by the way, please feel free to interrupt me at any time if you have questions, even throughout the talk. So let me just begin very broadly by saying that, of course, everything I'm going to say today is motivated in the background by our interest in the gravitational signals emitted during collisions of compact objects. By now, experiments like LIGO and Virgo have detected dozens and dozens of signals emitted, particularly by coalescing binaries, both black hole mergers, these blue dots, and neutron stars, which would be these orange dots here. And of course, new experiments and a new generation of experiments is planned for the near future. So this ongoing and future activity has stimulated the theoretical community to devote renewed effort in developing methods to come up with predictions for these gravitational wave signals. Now, in particular, whereas in the last phases of typical mergers, gravitational interactions are very strong because the two objects are very close together, and therefore, essentially, the nonlinearities of the Einstein equations are such that the only way to resolve the dynamics of the system is to resort to numerical simulation, so numerical relativity. In situations in which one can identify a small parameter, in which one can apply a perturbative scheme, analytical approximation methods become available. In particular, the most well-known and well-studied approximation is certainly the post-Newtonian expansion. This would be an expansion in which the two objects are sufficiently far apart so that the interactions are sufficiently weak, and also that the two objects move sufficiently slowly. This is schematically the regime one is looking at in that case. And in fact, this expansion is the best possible one for quasi-circular mergers in which the two objects move on approximately circular trajectories. And therefore, the Viriat theorem ensures that these two parameters, so essentially the potential energy and the kinetic energy, are of the same order and therefore must be small simultaneously. Another approximation scheme is instead the post-Minkowskian one, on which I'm going to focus in this talk, in which instead one only expands for small, as a slogan or as a power counting rule for small g, more precisely for weak gravitational interaction. This simply means that the typical size of the object, say roughly of the Schwarzschild radius, is much smaller compared to the distance between the objects, whereas this expansion remains agnostic concerning the velocities that the objects have. And in particular, this approximation applies equally well to bound and to unbound trajectories, in particular to scatterings, which are the most natural domain of application of scattering amplitudes applications, as I will motivate in the next slide. Another approximation that I would like to mention, although it will not play a very important role in today's talk, is the self-force, or essentially an expansion in the near probe limit, in which one expands in an extreme mass ratio, namely in the case in which one of the two objects is much much lighter than the other one, and then can expand in the ratio of the two masses, or equivalently in this so-called symmetric mass ratio nu. And by the way, this approximation is very powerful because it also applies in a strong field regime. It does not assume weak gravitational interactions at the other two. So, well, one of the key ideas that has motivated a lot of the recent progress and has led to some outstanding achievements is the following. And in fact, it's the one that I'm going to focus on also in today's presentation. Why don't we extract the post-Minkowskian gravitational dynamics from scattering amplitudes? So there are essentially a couple of reasons why this idea should sound rather reasonable. Well, the first one is that, as I already mentioned, this post-Minkowskian expansion uses as power counting parameter the Newton constant. And so it is very reasonable that, for instance, the leading post-Minkowskian term could be extracted from the tree-level amplitude, which is of order g, say, and then the next to leading correction of order g squared should be extracted from the next to leading amplitude, which is of order g squared itself. So this would be the one loop, and so on. And in fact, today's calculation, following this logic, essentially have reached a state of the art of g to the fourth, namely 4 p.m., and in fact, ongoing work. Work on the g to the 5 is ongoing. Another reason is that the post-Minkowskian approximation does not assume small velocity and therefore preserves Lorentz invariance, which is precisely one of the pillars of our formulation of amplitude and of quantum field theory in general. Moreover, just as a comment, although today we are going to focus on scatterings, which is the type of systems for which gravitational amplitude predictions are most naturally suited, a lot of the information that can be learned and has been learned for scattering problems, for unbound trajectories, can in fact be exported to bound trajectories that are of course more motivated from the phenomenological side. In various ways, one can, for instance, make an ansatz for the effective potential and then export it to boundary conditions in which the objects are bound, or go through an analytic continuation, as in particular pioneered in the papers by Rafael Porto and collaborators. Very well. So just as a final piece of motivation before going into the main part of the talk, I just wanted to mention in a slide some list of recent progress. This is by no means an exhaustive list. This is just to sort of whet your appetite and motivate why we are interested in all this business. So focusing in particular on the deflection angle or on the total momentum transfer, or so-called impulse, that the two objects experience during a classical scattering, the leading and subleading order calculations had been done by pure GR methods. So really by just sitting down and solving with pen and paper the Einstein equations and the equations for the particle trajectories to leading and subleading order back in the days, in particular in these two papers. And as you can see, since these amplitude or quantum field theory based methods joined the game, progress has started becoming rather rapid. 2019, 18, 19, the calculation I thought the subleading order was reproduced from amplitude methods, and then there was this outstanding breakthrough of the two loops, so leading next to leading order calculation of the deflection angle in 2019 by Byrne and collaborators. And then, as I mentioned today, also the order g to the fourth has been calculated. And so this set of results has motivated renewed interest in another observable, which is instead the waveform itself. So this would be really the signal that would be measured by the detector, by LIGO and Virgo, in the presence of a scattering. And again, the leading order was obtained a long time ago, and more recently it has been revisited and streamlined, simplified by quantum field theory inspired word-line methods or amplitude methods, and also extending to cases with spin. And since last year, in March, when a series of paper published the next to leading order result for the 2 to 3 amplitude at one loop, essentially the dynamical information to calculate the first subleading correction is available. So as I mentioned, the logic is that, for instance, this leading, subleading, subsubleading, etc., correspond to calculation of the 2-to-2 amplitude at various increasing loop orders. It would be the 3-level 2-to-2 amplitude, etc., etc. The Kovacs-Centaur result can be obtained from the 3-level 2-to-3 amplitude with one graviton emission, as discussed in these papers. And the idea is that, okay, from this 2-to-3 one-loop amplitude, one can extract, in principle, this subleading correction to the waveform. However, as we will see, one needs to do something with this amplitude. One cannot just take it out of the box and use it. So this would be part of the first. The first part of the talk will be devoted to how one should exactly use this ingredient in order to get to the observable. Another piece of motivation for today's presentation is the fact that using the data contained in these papers here, Bini, Damour, and Veralico in September 2023 extracted some predictions for this subleading waveform, focusing in particular on the post-Newtonian regime. So although the expressions here are valid for generic velocities, they focused on the small velocity regime. And then in that case, one can compare with more well-established techniques to calculate waveforms, in particular this multipolar post-Minkowskian / post-Newtonian expanded formalism. And although they found agreement up to some post-Newtonian order, which I will review, they also found some mismatch, in particular at 2.5 pn. Again, I will try to explain a bit better what this nomenclature actually means. This can be a bit confusing, especially the first time one hears about it. But essentially, one of the main messages of the talk would be to clarify whether or not these mismatches are actually solved. Very well. So if there are no questions, let's say, on the general pictures, let me then directly move to the first part of the talk, which has to do with extracting observables from amplitudes. And as I was mentioning, to begin with, I will focus on a case study, which is more well treated in the literature, which is the 2-to-2 dynamics, and in particular the impulse, or if you want, the deflection angle. So this observable can be extracted from a 2-to-2 elastic amplitude, which I'm depicting here. And of course, this is a function of the two familiar Mandelstam invariants. Here I'm using a notation which is a bit adapted to our problem, in particular this parameter sigma, which is related to the total incoming center of mass energy, is more precisely the Lorentz factor of particle 1 as seen from the rest frame of particle 2. And the other is related to this momentum transfer small q. So if you want, q squared will be equal to minus t. Now, from this fundamental object, one can extract information, as I was mentioning, about a classical process, which I'm instead depicting in this way. So this is the process I was mentioning in the first few slides. Two objects come in with momenta p1 and p2. Here I'm using this notation in which all momenta are formally regarded as outgoing, but p1 and p2 are actually the incoming ones. So the particles come in. They initially have some impact parameter bj, orthogonal to their velocities. They interact, and therefore they deflect. And the observable we are after is this capital Q, or equivalently, if you want, the deflection angle theta s. Now, let me mention that there is a slight, as you can see from the picture, there are two slightly different frames, or two slightly different set of reference vectors that one can employ. One is really the set of vectors anchored to the incoming state. So if you tilt your head just a little bit to the left, it's P1, Bj, P2. But as you can see, a more symmetric one, which will play a role in the following in this presentation, is instead this P tilde 1, Be, and P tilde 2, which essentially is a, let's say, average, or for reasons that will become apparent shortly, let me call it eikonal reference frame. And just to be a bit more precise about the regime in which we are interested in. So at the beginning I was mentioning we are interested in this regime in which gravitational interactions are weak. More precisely, this means that Gm over B, every time I just write B means that it's not relevant with Be or Bj. So the ratio roughly between the size of the objects and the typical separation should be small. This means that we are in the post-Minkowskian regime. And also we are in the regime in which classical gravitational interactions are relevant. If you want, this means that the Compton wavelength should be much smaller than the size of the curvature produced by these objects, so the Schwarzschild radius again. Or if you want that this dimensionless ratio should be very big. In fact, if you try to plug in the values for typical black holes of astrophysical nature, this ratio is stupendously large, something like 10 to the 78 or 79. So, of course, the classical approximation is very well suited to studying these very, very massive objects. And as a reminder, this parameter sigma is going to be the relative Lorentz factor. Very well. So what do we do, for instance, in order to extract the impulse from the 222 amplitude? Well, before discussing that in detail, let me just recall some properties of this 222 amplitude at 3 level and 1 loop. So at 3 level, of course, this is just a very simple rational function. Here I'm writing it down. And in fact, since we are interested in the regime of large B, and as you will see shortly, Q, this momentum transfer in each amplitude is dual by a Fourier transform to B, it means that we can also restrict to small q in the amplitude in momentum space. And moreover, since via Fourier transform any analytic term in q squared would correspond to a delta function localized contribution in position space or in impact parameter space, we can safely disregard any analytic contribution like q squared to the 0, q squared to the first power, etc., because these simply vanish for large B, for B strictly positive if you want. At 1 loop, instead, we have a bit more structure. So there is a real part, which I'm writing it down here. Note that this is obviously instead a square root. So this will be the square root of q squared, which is non-analytic. And then there is an imaginary part, which is instead fixed by unitarity to be just a convolution. This is a way of depicting the convolution of 2 3-level amplitudes, in which the exposed lines are all on shell. You should imagine that this is a phase space integral of the product of two 3-level amplitudes. So this is the object in which the dynamical information to calculate the deflection angle to leading and subleading order is encoded, but there is some work to do in order to extract it. Let me briefly recall it. So one way, which builds on is based on the approach proposed by Kosower, maybe, and O'Connell, sometimes also called KMOC or KMOC, is the following. Well, you are interested in calculating a classical observable, so you should build that observable. In particular, in this case, we're interested in the momentum of particle 1. Let me call it P1 mu, the operator that measures the momentum of particle 1, and consider the difference between its expectation value in the final state and in the initial state. The final state being simply given by the action of the S matrix on the initial state. This is conceptually very transparent, and in fact, you can, via some steps that I'm skipping, but I'm happy to provide more detail if you're interested in offline. You insert the operator, you insert the S matrix, you decompose it into 1 plus IT, and the matrix elements of T are simply the amplitudes that we all know and love. Using this, you can rewrite this as the Fourier transform, so this tilde is going to denote the Fourier transform of a quantity I mu, let me call it a momentum space kernel, which, as I was mentioning, has a 3-level and a 1-loop contribution. The 3-level is just the 3-level amplitude times q mu, of which we then need to do the Fourier transform as written in this formula. The 1-loop level instead has 2 contributions. One comes from the real part of the 1-loop level amplitude, and then there is a cut. This contribution that I'm depicting here, as you can see, it's related to this cut here, but there is a prefactor on which we are also integrating. So L mu would be the integrated momentum here that comes from the insertion of the operator. So this is all relatively simple. Let me sketch the final result of the calculation. As I was mentioning, we are instructed to multiply by I and take the Fourier transform. So at 3-level, this is the result that we find. Of course, multiplying by IQ mu in momentum space is equivalent to doing a derivative in position space, and this is the result. And the 1-loop level, we have 2 contributions I was mentioning. One is very similar, IQ mu times real part, again, derivative of the real part Fourier transform, and this is the result. And for the cut, we have to do the calculation. Let me not bore you with the details, but this is the final result. So putting together these 3 pieces, 1, 2, and 3, one finds the leading order and the subleading order contribution to the impulse. And this is, of course, in perfect agreement with all these papers I was mentioning from the 50s and 60s. Now, I want to draw your attention to the fact that the momentum transfer to leading order is aligned with Bj, or more precisely anti-aligned. Whereas to subleading order, it has a component along Bj, but also has a component along these initial velocities. So let me go back to the drawing. And from the drawing, it's kind of obvious, right? Because to leading order, since this deflection angle here is small, this would be theta s half, but theta s in the post-Minkowskian expansion is very small. So to leading order, one can pretend that Q is aligned with BJ roughly, right? To the first subleading order, instead, one needs to start paying attention that Q is not exactly aligned with BJ. It has a component along BJ, but it also has a component along the initial velocities, this longitudinal component, and this is precisely taken into account by this formula here. And by the way, this calculation was performed in great detail already in papers for instance, in this nice paper in 2021. Let me now compare this with another way of doing the calculation, which is based on the eikonal exponentiation. In this approach, which is a bit different, one first performs the Fourier transform of the full amplitude, and notices that in the Fourier, in impact parameter representation, the amplitude exponentiates. It's dominated by the exponential of a large phase, this delta, which itself has a 3-level and a 1-loop contribution. And by a simple stationary phase approximation, the impulse is just given by the derivative of the eikonal phase. And this is true to leading and to subleading order. So one goes through the procedure, calculates delta 0, delta 1, here are the expression, takes the derivative, and this is the result at leading and at subleading order. Now, as you can see, here we seem to be missing a piece, right? Because here we have the leading order aligned with B, and then the subleading order, which also seems to be aligned with B. So where is the piece along the initial velocities? Well, there is a small difference in the notation here. This is BE and not BJ. So again, going back to the picture, you see that if we pick BE, somehow BE seems to be a better reference vector, right? Because Q is exactly aligned with BE, not only at leading, but also at subleading order. And in fact, that's precisely what happens. So now if you take into account the rotation between BE and BJ, you can see that the two expressions that we have obtained from the two formalisms are exactly the same. So just to reiterate, this would be the result in the KMOC approach, which is expressed in terms of the initial velocities and the initial impact parameter. This is the result from the eikonal approach, in which you express everything in terms of the, say, average or eikonal impact parameter, and the two exactly agree. And moreover, the crux of the matter is this term highlighted here that comes from this cut. You remember this two massive particle cut, and this is precisely the culprit that takes care, let's say, of performing this rotation. There is a way of writing it down in an invariant way, but basically this means that this cut is simply performing an infinitesimal rotation of half the deflection angle. So I spent some time on this long excursus on the elastic case, but this is, as you will see in a second, this will be very useful for us in a second when we now deal with the 2 to 3 case. So now we have this 2 to 3 amplitude with one extra graviton emission. So there are more invariants, not only sigma, but also omega 1 and omega 2, which have to do with the frequency of K of the graviton as seen from particle 1 and particle 2. And from this guy, we want to extract the amplitude, the waveform, not only to 3-level, but also to 1-loop order. So what do we do? Again, let me start by reviewing the properties of this 2 to 3 amplitude. This has a 3-level contribution, which is a very simple rational function, and then a 1-loop contribution, which has a real part in complete analogy with the elastic case, plus some cuts. And by unitarity, the imaginary part is just given by I divided by 2, the sum of all the cuts. These are all the cuts that we have, and notice that you have some two massive particle cuts, in which, as you can see, I'm cutting the blue and the green line, which are the massive particles, and also some, let me call them Compton cuts, in which you instead cut a graviton. Now, this is the amplitude. Now, to calculate the waveform, we need to follow either of the two approaches I was mentioning before. Let me follow, for instance, the KMOC approach again. In this case, we are interested in the gravitational field. So the operator that we should insert in the final state is not the impulse or the momentum of particle 1, but really just the canonically quantized metric fluctuation, or let's say the graviton operator. One goes through this procedure and finds that one can express the final expression, maybe the final result for the waveform, in particular the frequency domain waveform. Omega here would be the frequency of the graviton, and U would be the retarded time at which the gravitational waveform is measured, R the distance from between the detector and the source. And this is again the Fourier transform of a momentum space, let me call it again kernel, W. At tree level, the kernel is precisely equal to the tree level amplitude. At one loop, instead, there is a difference. So the one loop kernel of which one should do the Fourier transform in order to get the waveform is not just equal to the one loop amplitude, but it's slightly different. In particular, there is this minus sign here. So whereas in the amplitude, just the sum of all cuts appear, in the kernel, the difference of the S-channel cuts, or the two massive particle cuts, appears. And in particular, this is crucial in order to ensure cancellation of singularities. I mean, the amplitude is not a well-defined observable, and in the classical limit, it is actually singular. And this is precisely due to this guys here. The fact that in the kernel the minus sign appears ensures the cancellation of these divergences. And this was also observed in the papers I mentioned dating back to March last year. However, it was later observed that this cancellation does not simply leave behind zero. It leaves behind a classical contribution, so a contribution of, let me call it, S minus, that should be taken into account. And okay, now I will not provide any detail on this step, but what we can show is that in complete analogy with what happened in the 2-to-2 case, this cut, when comparing the two reference frames, right? Let me go to back to the picture. So this is a prediction that we have obtained in the KMOC approach. So it should be naturally expressed in terms of initial velocities and initial impact parameter. But what this cut is doing for you is that it's simply implementing the rotation between the incoming velocities and initial impact parameter and the eikonal velocities and eikonal impact parameter. This is this contribution here. Plus a contribution that can be reabsorbed by adjusting the origin of retarded time. So let me not dwell too much on this, but the bottom line is that if one neglects this S minus, the only difference is that the result should be interpreted in terms of the average impact parameter and average velocities. So P tilde 1, P tilde 2, and or U tilde 1, U tilde 2, and PE. And okay, one also has to perform a translation of the retarded time in this way. But as you can see from here, and as will be apparent in a few slides, hopefully the origin of retarded time is in any case not a prediction. It comes from amplitudes. In fact, it's even infrared divergence. So in any case, the instant at which the gravitational radiation arrives is not observable. Only the difference of let's say the time difference between the peak and the valley in the signal is. So the bottom line is that instead of considering this more complete KMOC kernel, one can consider an eikonal version of this KMOC kernel in which this cut is not present. Let me call it W eic, in which only B1, so the real part of the amplitude, and the Compton cuts, these two beasts here, are present. So this is somehow one of the main punchlines. And in fact, this formula that we had derived in December has been recently confirmed in a paper that also came out a couple of days ago by Bini, Damour, De Angelis, Geralico, Herder, Sheroiban, and Teng, by calculating both sides to higher order in the post-Newtonian limit. Very good. So now that we have understood that we don't need to care about this guy here, let me instead focus on the other ones, on the other ingredients. So as I was mentioning, the tree level doesn't present any special challenge. It's a relatively simple rational function, which we can deal with in very simple ways. Let me instead focus on the one loop pieces. So as I was mentioning, there is a real part and an imaginary part dictated by the Compton cuts. The real part has itself two pieces, one which is very simple, this would be 1O, because it's fixed again in terms of the tree level. As you can see, it's proportional to it times a function that is only a function of sigma, actually, so of the velocity, if you want. And then there is a genuinely one loop piece, this B1E, which, as you can see, is a bit more complicated, has some square roots, so you can see that it's a genuinely one loop beast. These functions A are going to denote some polynomials, which unfortunately do not fit in one slide and whose natural habitat is the ancillary files of the papers of March last year. In particular, I'm going to focus on the one given in this paper here. Of course, they all agree with each other, but let's focus on the one given in the paper by Herder, Schroeban, and Tang for definiteness. And then you can see here the appearance of this calligraphic Q1, which is appears in the denominator, so it suggests that it should be associated to some singularity, but actually it's a fake singularity of the result. So if one projects on a physical polarization and takes the limit Q1 going to 0, one finds that there is actually no singularity associated to it. So that's why we call it a spurious pole. And okay, here I'm showing explicitly the contribution from this mass structure, but there is, of course, another one obtained by particle interchange symmetry. Finally, the most complicated ingredient are the Compton cuts. Particularly here, let me discuss it for C1, so the one in which the graviton is attached, is re-interacting or rescattering, as sometimes one says, against the blue line, so mass 1. And okay, it has a bit more complicated structure. There is again a piece which is very simple because it's fixed by the exponentiation of infrared divergences to be proportional to the tree-level amplitude. And then there is, a host of, polynomials divided by spurious poles and then some logarithms. This is just to give you an idea, a rough idea of the structure that these guys have. And even more spurious poles. As you can see, there are also this calligraphic P and calligraphic Q here, which appear to higher powers. In particular, here, there is the highest power of spurious poles that we have to deal with. So the first thing that I have to discuss is about this infrared divergence. So as I was mentioning, this is fixed by the exponentiation of infrared divergences that goes back to Weinberg. And so one way to deal with it is to exponentiate, so to realize that since it's proportional to the tree-level amplitude, one can rewrite it in this fashion by factoring out as a divergent phase and defining a regulated kernel in which now this C1 plus C2 is infrared finite. It's given by this expression. Now this has a subtlety that is important for us, namely not only this plus I over epsilon, etc., cancels this divergence here. As you can see here, it has a minus sign, whereas here it has a plus sign. But also it induces a modification in the finite part, which is due to the fact that A0 here must be the tree-level amplitude calculated in d equal to 4 minus 2 epsilon dimension. So here epsilon is the Dimereg parameter, of course. In particular, in A0, there are some trace parts that come from the subtraction of dilaton exchanges, and therefore A0 has an order epsilon part, and by the epsilon over epsilon interference between these two factors, there is also a slight modification in the finite part of the resultant one loop. So this is a subtlety that, as I was mentioning, will play a role in the following. And okay, once this has been dealt with, again, this divergent phase can be reabsorbed by shifting suitably the origin of retarded time. As you can see here, you can just shift u to u minus ge over epsilon, essentially, and obtain a finite and well-defined prescription for actually calculating the waveform. This, in fact, has been realized in papers by Ross, Goldberger, and Porto, also already in the post-Newtonian literature. Very good. Now that we have a clear idea of the calculation that we have to do, so just to reiterate, we can just focus on the real part of the one loop amplitude and the Compton cuts of the one loop amplitude, and we can do away with the infrared divergences in this way. Let me show some explicit results. Now, of course, the best possible thing to do would be to just perform this Fourier transform exactly and obtain the result exactly, but this is complicated and therefore result to limits. Well, Another piece of motivation is that in the two limits I'm considering today, one can compare with different approaches, in particular with the literature on soft theorems, which give universal predictions for certain pieces of the amplitude or the waveform for small frequencies, and with the post-Newtonian literature, in particular with the Bini Moore and Geralico. So, for soft limit first, I will not go too much into the details. After all, this is a bit of a technical essentially calculation that one needs to do. One needs to sit down, take the soft limit, perform the Fourier transforms, and obtain the predictions. Let me just mention a couple of subtleties or of interesting steps in this procedure. So we are after, as I was mentioning, the small frequency, or more precisely, omega being much smaller than the typical frequency scale of the problem, which is 1 over b, the impact parameter. And in particular, we are targeting non-analytic pieces in omega, because these are the ones, in particular, is omega to the -1, log omega, omega log omega, because these are the ones that affect the large time, if you want, large retarded time behavior of the waveform in time domain. And okay, one needs to be careful when performing this limit, because of course, simply sending omega to 0 by keeping the momentum transfer fixed, since we are performing this limit already in momentum space, doesn't give the full result, right? One needs to pay attention to two different regions in the integration over the over Q. So of course, we have in mind that we have to integrate over Q because of this Fourier transform I was mentioning, which is roughly a two-dimensional Fourier transform of this kind. Now, in this region 1, one can simply send omega to 0 and keep Q of the same order of 1 over b. And then in this region, the amplitude dramatically simplifies and all Fourier transforms become elementary. And there is also another region, which omega is of the same order as momentum transfer, and both are much smaller than 1 over b. In this second region, the amplitude does not simplify at all, but luckily one can expand out the exponential in the Fourier transform. So effectively the Fourier integral turns into an ordinary integral, and all, especially at one loop, at tree level, the integrals become very simple of this form. So after doing that, let me show you finally some results. Well, the leading soft term is given by this expression, both at tree level and at one loop. So Q would be the tree level and the one loop momentum transfer. So the one that we calculated in the first part of the talk, actually. The tree level gives inserting the tree level Q gives the tree level 1 over omega behavior, and inserting the subleading impulse gives the one loop 1 over omega behavior. And this formula agrees perfectly with the well-known memory effect. In particular, it matches the form given in the soft theorems by Sen and collaborators. And similarly for the log omega term, which is given by this expression here, this is the tree level, this is the one loop part. Let me recall that these are the that all velocities and impact parameters for the tree level parts must be expressed in terms of the average impact parameter and average velocities in order to get this specific simple expression. And in this also matches the predictions by Sen collaborators, and similarly for this omega log omega square. In particular, a key simplification that comes about when focusing on these non-analytic pieces is that in these two regions, one can simply focus on one of the two, because by dimensional analysis, a log omega coming from one of the two regions must correspond to a log b coming from the other region in order to reconstruct properly dimensionless logs. So dimensional analysis is very powerful and allows you to just focus on the simpler region, which is the first one. Instead, to get to the next order, we also need an omega to the 0 piece, so analytic piece in the tree-level result, for reasons that will become apparent in a second. And as you can see, this beast already becomes considerably more complicated. Here, I'm not giving really the explicit terms of this G1, G2, G3. Again, this is just to give you an idea, the flavor of the result. And the reason why we need it is that then to get the one loop omega log omega piece, we need to plug it in. We need to plug in the expression for the omega to the 0 tree level inside the piece that had this log omega. So as you can see, going back to the expression for the Compton cut, there is an explicit log omega dependence here that multiplies the tree-level amplitude, and therefore we need to determine the A0 accurately also to order omega to the 0 in order to be able to get the omega log omega piece. So this is again, a schematic form of the result. Let me also mention that the tree-level omega log omega piece is also fixed by a result in the soft theorem literature for which we find agreement, whereas instead the omega log omega piece is, in a sense, not universal, or if you want, it's not fixed by non-soft theorem, so you just have to do the calculation and find this ugly expression. So how do you know that it's correct? Well, we don't have a prediction coming from soft theorems, but we do have predictions coming from the post-Newtonian literature. In particular, in the paper I already mentioned by Bini, D'Amore, and Geralico last year, they also published an expression for the omega log omega term expanded in the small velocity limit, and with which we find perfect agreement. In particular, the up to and including this 2.5 pn term. However, the agreement is not obvious. In particular, if one starts with the expressions of the amplitudes in order to do all this procedure with the expressions given in the papers back in March, one doesn't directly land on the expression given in this paper here. One lands on an expression which differs by that one by BMS supertranslation. So this is one of the transformation of the asymptotic symmetries of asymptotically flat spacetimes, and in particular, it means that one is landing in a frame in which the asymptotic shear doesn't go to 0 at infinity, at minus infinity, but rather to a constant fixed by the initial velocities. And this was already noted by Veneziano-Vilkovisky in the approach by Bini et al. Instead, coming from amplitudes, typically, unless one includes certain static modes, but let me not go into details there, typically one lands on the supertranslation frame, which is associated to a shear that goes to 0 at minus infinity, and the two precisely differ by a supertranslation. So applying the Veneziano-Vilkovisky supertranslation, we found that our amplitude-based result precisely maps to the MPM PN expanded result of Bini et al. So this is a first signal that the mismatches that were pointed out in that paper are actually due to the fact that the results were calculated in different frames. The first frame was, the first difference between frames is due to this rotation, but in fact this rotation had also been realized in the paper by Bini et al. In the post-Newtonian limit, and another difference is instead related to this supertranslation here, on which, by the way, the paper that Bini and other collaborators published a couple of days ago, they have an interesting perspective owing to this soft zero-frequency gravitons that was mentioned. So this concludes the part about the soft limit. Now, very quickly, just to conclude, let me instead deal with the post-Newtonian limit. So now the objective is to see whether performing this rotation and this time translation and this super translation is enough to get agreement between amplitudes and post-Newtonian literature, even without doing the soft limit. So considering generic frequencies, but sticking to small velocities. So this, just as a matter of notation, let me remind you that in this post-Newtonian expansion, one expands for small velocities, in particular P infinity is small. And in fact, also omega, the frequency must be of the same order as P infinity. Essentially, the reason is that if one takes the initial velocities to be very small, then the energy available to radiate gravitational waves correspondingly decreases. So the sensible thing to do is to scale two things in the same way. And that's why non-trivial dependence on the frequency is retained in the end. And as a matter of terminology, by convention, in particular by his virial theorem we were discussing, in the post-Newtonian counting, a power of the Newton constant increases the post-Newtonian order by 1 unit, whereas a power of this lambda of the velocity, if you want, increases just by half a unit, in such a way that if you have odd powers of lambda, you can have fractional post-Newtonian order. That's why sometimes we talk about 2.5 or 1.5 pn. And this is a picture of the reference frame we are adopting. So the scattering plane is the xy plane, and B is aligned with X, and zeta is the direction orthogonal to the plane. So what we did was to take again, the various ingredients of the kernel, expand them for small velocities, performing the Fourier transforms, and then express the result in these conventional multipoles that people in the post-Newtonian literature often employ. So these are essentially, this is a decomposition of the waveform into tensors with definite eigenvalue under the Laplacian, essentially. But essentially, they are collections of symmetric trace-free tensors that do not depend on the angles, and for which you can reconstruct the angular dependence by summing in this way over the unit vector n and the polarization with which you perform the transverse traceless projection. Another word about the notation is that omega is a variable that scales in the post-Newtonian limit, so it's convenient to introduce this dimensionless variable omega b divided by p infinity. It does not scale, right, with lambda. So again, I will not show many explicit results, just a few sample ones, but let me mainly mention the strategy that we employed to perform this calculation. Okay, so one simplification is that in this post-Newtonian limit, all Fourier transforms become trivial. They can be all performed in this way, using this representation in terms of Bessel functions, modified Bessel functions. And drawbacks are instead related to the fact that the various variables, this sigma, omega 1, omega 2, depend in a rather non-trivial way on p infinity. So when one wants to take the limit, things can become very complicated very quickly. But there are tricks that one can use. For instance, one can expand out the elementary variables to high order and then substitute the expansions at the level of invariance. This helps the machine a lot. And the main complication is related to the presence of these spurious poles that I was advertising. The reason is that each of these spurious poles scales in a bad way. It goes to zero with a high power of p infinity, and also large powers of the spurious poles appears in the denominator, which means that you are forced to expand the numerators to very high order if you want to get the correct result. So this problem is especially severe for the Compton cuts. So what we did was to fix that by making an ansatz for the final result of the expansion. After all, we know its structure thanks to the exact post-Minkowski representation, and we know that up to some square roots that we can factor out, the result must be a simple rational function of which we know the denominator. So we can make an ansatz for the numerators and simply fix it by evaluating the limit numerically on a suitable number of points. In particular, we had to, for instance, for a given mass structure and tensor structure at the highest order at which we went, so 3pn essentially for the Compton cuts, we only had to use about 180 points, so nothing very, very fancy was needed. Another interesting and complementary approach was instead of employed in the other paper I was mentioning by Bini and collaborators, where they instead exploited a clever rewriting of the cuts in order to overcome this difficulty. So, having said all that, let me be a bit more precise about what we did. In particular, it's convenient to split the various pieces of our one-loop kernel in this way because of the different scalings with the velocity. In particular, it's convenient to split the easy part of the three-level kernel in this way, because as you can see, this one scales with a much higher power of velocity. And then what we did was to expand each of these ingredients at next to leading order. So the first four powers in lambda. Again, to be a bit more precise, let's say, for instance, we focus on the quadruple contribution from each of these ingredients. The quadruple would be the first of these symmetric trace-free tensors, so the leading one. For instance, that's the one that you deduced from the famous Einstein quadruple formula. But of course, this gives you many more corrections to that. So in each of these ingredients, you see that the lambda expansion starts to slightly different powers. Let me not go too much into the details, but one important feature that I wanted to emphasize is the fact that the relative fractional corrections to a quadruple and in general to a given multiple only come from two pieces of the kernel. This would be a very simple piece related to the tree-level amplitude here that has a factor of pi in front, this guy here, and precisely the famous Compton cuts. So these are really the interesting part of the calculation, which start at 1.5 pn, and for each multiple they receive a correction size by an additional power of lambda squared. So in practice, what we did was to calculate the leading contributions to U2, 3, 4, and 5 and V2, 3, 4, and also the first subleading contribution, as you can see from here to U2, and also to U3 and V2. Again, just as the full set of multiples you can find in the ancillary file attached to the paper, but just to give two examples. One very easy, the Newtonian quadruple, the one that comes from the Einstein formula, takes this form. These are these Bessel functions I was mentioning, and these are the components of the quadruple. And one which is a bit less easy to get is instead the 1 pn correction that comes from this guy here, BE, which as you can see starts at 1 pn. This is given by this expression here, and for instance, one component of the first subleading correction to that is this one. For this one, we also performed an independent check from the multipolar post-Minkowskian side. So let me now discuss checks before concluding. So one check is to take all the multiples that we got and substitute them into the formulae for the emitted energy and momentum. And by doing that, we find these results, which as you can see involve these complicated coefficients that were all published in particular in papers by Birida, Moore, and Gerarico, and with which we find perfect agreement. One part of these expressions of which I wanted to draw your attention is this contribution here to the emitted spatial momentum, in particular this 1491, etc., etc. This is the component of the radiated momentum along the impact parameter, which as you can see starts at the next order in G. There is no such component. E mu is the component along the initial velocities, whereas B mu is the component along the impact parameter. It starts at order G to the fourth and is sensitive in particular to these Compton cuts that are in a sense the most interesting part of our calculation. And moreover, this subleading piece is also sensitive to those epsilon over epsilon contributions, right? You remember when exponentiated the infrared divergences, we had to take care of this small modification in the finite part. Well, if we hadn't gotten that wrong, we would have gotten a wrong result for the total emitted momentum, which means that's not a choice of scheme or something that that you are allowed to change if you wake up and feel doing something different. That would have been a mistake. But okay, using this procedure I mentioned, we find perfect agreement with all the literature, in particular with this next to leading order emitted momentum. And now finally, the most interesting check is to just directly compare what we get for the Compton cuts. So the C-reg, it's very interesting because compared with what? With the prediction that come not from amplitude, but from the most multipolar post-Minkowskian framework. So in this approach, you have to take into account several different contributions that affect these half integer Pn terms. In particular, this first correction to the quadruple is sensitive to the following. A contribution that comes from the tail formula. This is some effect precisely due to this rescattering. So also very physically, it makes perfect sense that it should enter the interact, let's say, with these Compton cuts. These are, after all, radiation that is emitted and then rescatters precisely against the curvature induced by either particle. This is especially there is this log, which we recognize agrees perfectly with the log we had, for instance, in this expression here. And then there are some magic numbers, this kappa L, which are sometimes called harmonic numbers, which predict in particular the leading order in the mass ratio for all the time reversal odd effects, and which from the amplitude perspective is kind of a miracle. I mean, there is no reason why the leading order in the mass ratio of this beast here should be proportional to the tree level times some magic number, but that's just what happens. And then there are nonlinear effects which also affect the order nu squared, the square of the mass ratio. And these are a host of different expressions that you had to add up, trusting the post-Newtonian literature. In particular, they appear with funny coefficients like 5 or 7 or whatever divided by 15, etc., etc. And you have to take them all into account. Physically, they come from the nonlinearities of gravity. So by the fact that in this framework, this why it is called MPM or multipolar post-Minkowski is that each multiple comes from also from products of lower order multiples, right, which come from self-interactions of the gravitational fields. And finally, there are some generally time reversal odd effects in the trajectories themselves. For instance, radiation reaction, for which you have this correction to the trajectory that you have to plug in the multiple when you do the calculation. Well, we find that after adding up all these magic contributions to the quadruple, we find exactly the same result that comes from the amplitude side, up to and including 2.5 pn. So this solves the tension that was highlighted in the paper by Binida Moore and Geralico last year. And again, the two subtleties to be taken care of are exactly the same as we were saying earlier on. So one is the super translation. So the fact that the amplitude result more naturally seems to land on one super translation frame, and to move to the MPM one, you have to do the Veneziano-Vilkovisky super translation, the same one that we had in the soft case, by the way. There is no difference there. And the other one is this epsilon over epsilon contribution. In particular, as I was mentioning, it was crucial for this guy, but more generally, it affects this guy here, and therefore it would spoil the agreement with MPM if we were to change somehow the dim-right prescription to something else. So, in essence, this concludes what I wanted to say, and you also mentioned that the same conclusions were also reached in the paper that appears simultaneously by Bini et al. Very well, so let me conclude just by reiterating the main messages. Both the eikonal and the KMOC approaches agree in a, let's say, non-trivial way once these subtractions are properly calculated and interpreted. So in particular, there is this B eikonal versus Bj or B initial that is crucial. The main message is that the KMOC formula all land on the initial, the frame anchor to the initial moment and initial impact parameter, whereas the eikonal one provides the one anchored to the average or eikonal ones. And the comparison with the soft and also with the PN result is interesting, technically and conceptually. In particular, there is full agreement up to and including 2.5 PN once you calculate both results in the same frame, in the same BMS frame in particular. So for the future, there are, of course, several interesting avenues one could explore. For instance, is this choice of BMS frame relevant in other contexts, or as we expect, for instance, when you include also tidal effects or spin, or when you do comparison with other frameworks, for instance, numerical relativity or NRGR. Another interesting point is whether or not it's relevant for bound orbits. Of course, it would be interesting to obtain analytical results beyond the ones that are shown here, so beyond soft and or PN limits, so for generic frequencies and velocities. Would be, okay, more conceptually, this eikonal exponentiation essentially, okay, I haven't delved into the detail here, but the underlying idea to get this eikonal kernel is to exponentiate not only the graviton exchanges via the eikonal phase, but also the graviton emissions by an eikonal operator, in fact, on which also our hosts here, Feng Lin and Karan, have worked. And so it would be interesting to see if this naive, let's say, coherent exponentiation of the emissions also breaks down at some point, or if it does. And okay, lastly, interesting points concern the possibility to analytically continue the results to bound trajectories, possibly large eccentricity, or also resumming the eccentricity, building on some recent work. And of course, an outstanding open problem is to go subleading and calculate the next to leading order waveform, which of course will require the 2 to 3 amplitude at 2 loops, which is a non-trivial challenge. So with that, let me stop here and thank you for your attention.
Okay, so thank you so much, Carlo, for the lovely talk. And Yeah, so I think we can take several questions at this point.
Can I ask a question?
People can just, please, Paolo.
In the soft case, you also need to do the BMS transformation. Is it true that or not?
Yeah, exactly.
Can you rephrase the question in another way? Instead of talking the BMS transformation, can you instead add the static modes and you get the same result or not?
Yeah, so that was I mean, we were thinking about that, but we didn't publish it anywhere. But that was done in the paper by Pini et al. On Monday. So they show that including the static modes in these cuts in particular precisely gives you this super translation. So you have two possibilities. Either you don't include them and you just use the results of the papers of Marsh last year, which did not include them, and then you land in the, let's say, Gabriele and Grisha frame, and then you do the super translation to compare with the Moore. Or, okay, if you want, you can go back, include them in the amplitude side, and then you directly land on the result of the Moore. That's
okay.
So it's complete analogy with what we had found for the angular momentum, right? You remember in 2022 also there. If you don't include, etc., you have zero angular momentum lost order g squared, but if you did include them, etc. So it's precisely the same. I mean, the novelty is that the difference in the final result is not a static contribution because of this convolution, right? So essentially this graviton is zero frequency in these contributions that you add. I don't know if you see the cursor.
Yes.
So this graviton here is zero frequency, but this one is not. So,
yes.
So it's a static contribution in the cut, which contributes to the non-trivial omega dependence of the waveform. And mutatis mutandis, this is what happens in this formula here. So the supertranslation in principle would have two pieces. One, which is this one, which is the static one. So T does not depend on time. But the one which is important for this comparison is this one, in which T is static, but then there is a derivative of the leading order waveform, which gives you a non-trivial frequency dependence. If you want constant term in time domain is non-constant, or in frequency domain, the convolution of a delta function and a non-delta function is not a delta function. It's a function.
Yeah.
That's
Thank you very much.
So related to this, this difference will contribute to the memory effect or not?
No, okay. The memory effect is really just about the difference between. Okay, let me try to. Okay, yeah, there are two things. Okay, this term here does not, because it's a constant, right? So of course, when you do the difference between u bigger, let's say u plus infinity and u minus infinity, you just get zero from this guy here. From this guy here, in principle, it would seem that you can have a contribution, but by inspecting what the super translation does, let me go back to the expression here. So you can see that since the super translation, since this piece amounts to this transformation, right, the infinitesimal version of this shift, and this means that in frequency domain you add a piece which is omega times t times the tree level, and the tree level has a 1 over omega. It means that it will not affect the 1 over omega, right? Because there is an extra omega. And therefore, it will not affect the 1 over omega piece in frequency domain, so it will not affect the memory in time domain. The first piece at which it appears in the frequency expansion is precisely this omega log omega here. So I think in Fourier domain, so in time domain, it means 1 over u squared, right? Because integral d omega of omega log omega, I think it goes like 1 over absolute value of u squared.
So in this sense, it will not affect observable, even they look different due to different choice of a frame. For symbolic,
Yeah, exactly. Yeah, sorry.
No, so a symbolic observable like a memory effect layer will not be affected by the gauge difference you choose.
No, but okay, exactly. So the memory will not, but somehow the shape of the signal will change a little bit. So it's not the memory, but it's some subleading order components in the large U expansion or in the small omega expansion. So I think this touches upon the question, which I think underlies your comment, right? So are super translations physical transformations, or are they gauge redundancies?
Yeah.
So
That's also
okay.
confused when people say, if I want to measure if this difference is measurable or not. Yeah, because you have different measure, you get different answer. Even they are just different by super translation. So which answer should I expect to make when I do the measurement? Yeah.
That's a very good question. I think Thibaut Damour and Gabriele Veneziano would answer two different things.
Okay.
So no, it's a very important question, I think. So okay, on the one hand, I think that the people doing multipolar post-Minkowskian and really just solving the Einstein equations from the source through the intermediate region and up to the asymptotic region, I think their statement is that the super translation frame is fixed and that you cannot choose it, and that the right one is the one that the Bini, Damour et al. Paper has. So after performing this super translation, on the other hand, there are considerations like the fact that, for instance, the angular momentum of the system in the far past only reduces to the ADM angular momentum if you are in the other super translation frame. So when you are in a frame in which the shear goes to zero in the far past. So there seems to be some tension in the physical interpretation of the two frames, and I'm not really sure what the answer eventually is. But these are very important questions, and I think also related to the memory effect, I think also people doing numerical simulations were finding that somehow if they were being not too precise about the super translation frame, in their simulations they were losing track of the memory effect. There were in particular talks by people at this workshop that we had in Queen Mary last year, and they were saying, no, but like if our simulation doesn't keep track of what super translation frame we are in, then our signal goes back to zero no matter what we do. Instead, if we want to find the step function, we have to define a quantity like the Bondi supermomentum and fix it, I don't know, to zero at the beginning and make sure that our simulation keeps it zero all the way. So I think there is a lot to learn but many people are thinking about these issues. So hopefully we will have some punchline about that.
Yeah, thanks. Yeah. Nice to know that opinion. Okay. Yeah. Yeah. So any other question?
I mean, if there aren't, I have a few, but I'll ask it in the end. Or I can ask an offline as well. That's fine.
I mean, I think you can go ahead.
Okay, so I mean, I didn't understand the point you mentioned about the cancellation that takes place between the S's, like in the Karen Huo paper that you mentioned. So
yeah.
You said there's a cancellation that's happening. So is this of the kind of like IR and UV divergences that they argue for, or is it some other kind of cancellation?
No, okay, sorry. Maybe I was not very precise in the terminology. So this is the expression. Now, it just so happens that separately S and S prime, if you consider the classical limits, so really just the H bar, small H bar expansion, each would scale, let's say, like 1 over H bar squared, just kinematically. But the difference, in the difference, this 1 over H bar square or super classical terms cancel. So this was already noted in the papers back in March. And in fact, the fact that the sum appears in the in the amplitude is consistent with the exponentiation of the eikonal operator. Because, right, you will have e to the 2i delta 0, which delta 0 is essentially the blob, the 2 to 2 blob, times the 3-level amplitude, which is the 2 to 3 blob. And the combinatorics is precise that you should have no factor in front. So delta 0, 2 delta 0 times 3-level. So the fact that there is 1/2 and the sum of these two guys, and the fact that the leading order add up, they cancel this 1/2, is, I mean, is one of the checks, if you want, of the exponentiation of the eikonal operator. On the other hand, okay, if you subtract the iteration in the eikonal approach, or if you consider the KMOC approach, it's important that after these subtractions, these superclassical pieces cancel out. Now, the issue that was present, I mean, there was a problem in the papers of March, and that was pointed out in the Caron paper, Caron et al. Paper, is that, okay, there is this cancellation, but after the cancellation, there is a leftover that you cannot throw away without discussing. So this is this leftover. And okay, now we understand that it is important precisely because otherwise you wouldn't know how to interpret the initial velocities and the velocities and the impact parameter. This piece is there to tell you that, okay, they should really be, in the KMOC approach, the initial velocities and the impact parameter associated to the initial state. Then, okay, what I was arguing for, and what is shown by this formula and is checked in this other paper, is that if you throw that away, you can do it, but the price to pay is that you have to interpret all the velocities and all the impact parameters as the eikonal ones.
Okay, so it's of the same character as the rotation you mentioned earlier between BJ and BE. So
precisely.
So BE is some kind of privileged choice, which gives you the it's a long queue, so it has some kind of a privileged role in these results.
Exactly. So the analogy with the 2-to-2 case is really striking, because already in the 2-to-2 you see that the expression that you find is simpler when you express it in terms of BE instead of BJ. You have one less term, and that's exactly what happens also in the 2-to-3. So you have one less term. You don't have this cut in the eikonal frame. Let me say it like that.
Okay, then to
follow. And in fact, I mean, it's a lesson that we learned also from Thibault et al., because they had already noticed it in the PN limit, that in order to match already at leading, like, Newtonian order, they had to pretend that the results of the papers of March had to be interpreted in this eikonal or average frames. So then what we did was to show that that's true for all frequencies and for all velocities, essentially.
But large impact parameters.
Yeah, sure. Still to this order in the post-Minkowskian expansion, so this order in GM over B, if you want, but for generic velocities.
And I also remember from that paper that they had like these generalizations of classical observables, right? Like you have, other than the standard unitary cut, they mentioned about some other kinds of cuts which are possible. Have all of these possibilities been accounted for in this analysis that you're talking about? This S, and is it always of this S and C kind, or is it something? It was a long paper, and maybe I've...
Yeah, no, it's a huge paper. The part I'm referring to is the one that most directly affects the waveform calculation. But no, I think they also have an understanding, which would be interesting to explore further, of the fact that, okay, as is usually said, I mean, they also proved it, but the naive interpretation of this KMOC business is that it turns amplitudes, which are in-out objects, into in, which means essentially turning Feynman propagators into retarded propagators. And that's I mean, it resonates with what I'm saying in a sense, because, sorry, I have to charge the computer. I mean, it resonates with this idea of, having the initial impact parameter and then determining everything from that, and instead having this average one. But that's just, I mean, a bunch of words. Of course, it would be interesting to see somehow why, I mean, if there is something deeper, you know, turning these cuts into retarded, you know, adding these cuts means turning the propagators into retarded ones. So maybe that is more precisely related to this idea of turning the average impact parameter into the initial one or something like that. But no, we don't have a complete discussion of all the possible cuts that you can have. Or yeah.
They had brought about some, I think, general structure as well, right? Like about different ways in which you can consider cuts to have observables. I think that was the end of their paper, the end of the some generalization of classical observables. But yeah.
Yeah, no, in fact, I think one of the points of the paper was that the crossing of certain amplitude doesn't give an amplitude, but rather an observable in the KMOC sense.
Yes.
So yeah, that's very interesting. And somehow all this business for them was just an application, was just an example. Like, and as an example, we can calculate the waveform. We get this.
Okay. Yeah. If I'm taking too long, I can take it offline, and email.
No, please. I mean, I don't have any specific constraint.
Sure.
Of course, people should feel free to leave, I guess, at some point. But
if people would like to leave, that's completely fine. Yeah. Then the next question I had was, you showed that the role of the C is to cancel out. It looked like it's canceling out IR divergences. So it plays a role similar to like the loop cancellation with the soft factor, which Weinberg talked about. So like you'd get a 1 epsilon from the Weinberg thing, and this Compton piece is giving you essentially the loop IR effect, which is canceling out. Is that what's going on, or is there something more?
No. Thank you for the question. I think the two things should be kept separate. So what happens here is that our observable, in the sense that we have to do the Fourier transform of this guy here. So let me say that this is the observable. As you can see, it's linear in the amplitudes. So precisely because we have, you know, eliminated this issue about the S minus cut, we have these ingredients, which are all ingredients that appear in the amplitude itself. We are simply just picking the cuts, the C1 and C2, and okay, the B1. Now, as you are saying, okay, by the Weinberg paper 1965, the cuts have divergences which are associated to exchanges of very soft gravitons between the external lines, in particular in this case between the graviton. So when one of these blobs has an exchange of a very, very infrared or soft potential graviton, they generate these divergences. So that's exactly what's happening. Now, the problem here is precisely that, unlike in the paper of Weinberg 65, we are not calculating, for instance, a cross-section or an absolute value squared. Because in that case, I agree with you, we would also have, together with these virtual contributions from potential gravitons, in the amplitude, we would also have phase space integrals of real graviton emissions, which can be very soft and can cancel this. The problem is that we don't have that. We have to integrate the amplitude, or let's say a cut that is already in the amplitude. So then that's why I was performing this discussion here, following the papers of Goldberger, Ross, Porto, etc. And also this was also realized in other papers in March. I'm not claiming there is much new here. Just you realize that you can rewrite the divergence in this way. So this is just a rewriting of this C1. In fact, I think I'm using the same symbol. I mean, of this W eikonal. You just rewrite it by noticing that you can exponentiate, of course, up to the order in G that we are working on, right? So if you want the check is that if I re-expand this exponent, I will get minus I over epsilon G E omega A0. As you can see, plus I over epsilon G M omega A0, so the two cancel. And the benefit is that in this way, you see by naked eye that you can reabsorb this divergence by shifting the origin of retarded time. So in other words, the interpretation of this divergence is, as far as I understand, is telling you that that the calculation that you did does not predict when the waveform will arrive at the detector. That you have to fix by experiment. So you fix the origin by saying, I don't know, when you have the first peak of your signal. But that's not something that the calculation tells you. Sometimes people talk about the time of flight. So even if you set up your experiment, your system in such a way that the minimum distance is reached at some point, then you're not able to predict how that point is correlated to when the waveform arrives because of this infrared divergence. So this is in some sense a renormalization. You just admit your ignorance about one piece of information, which is the origin of retarded time, and then the rest you can predict. Then you can predict the shape. So after you fix the origin in some way, you can predict, I mean, there will be a blip, I guess. There were also plots, right, in the other papers in March. The form of that blip you can predict. And so there is no cancellation between virtual and real. It's just virtual, and it's an infrared divergence that is there. You just have to discuss it in some way. The only thing that we are adding, sorry, just to conclude, in this paper and also in the other paper by the other group, is that, okay, not only you exponentiate this beast, but there are these cross terms, right? I mean, in hindsight, this is obvious because, of course, this formula must be interpreted all in dim reg, so in d equal 4 minus 2 epsilon. You're not allowed to put here the expression for a in d equal 4 because that's not consistent, right? So by consistency, you should subtract the whole thing here, including the epsilon over epsilon terms. So that's just a subtlety that was, I mean, the calculation in the post-Newtonian limit is really the first one in which you can nail down the subtlety very clearly, because it just so happens that these epsilon over epsilon terms in the soft limit are washed away. So you can see that if you just focus on the soft radiation, this epsilon over epsilon piece, you can again reabsorb them by shifting u appropriately. But that's an accident of the soft limit. So if you do the calculation, otherwise you find that they are important.
Yeah, this kind of gets me to the follow-up I had for this, which is that you had mentioned about the peak and the valley, the peak and the saddle that you have to take. So essentially what you're saying is you calculate, and then from there you identify the minimum, and that minimum tells you the origin for you for the retarded time. Is that roughly how?
I would interpret it in this way. Somehow, exactly, somehow this procedure only determines for you the shape of this function as a function of u and of the angles, but it doesn't determine for you where on the time axis you are allowed to, I mean, where you should place it. So you can fix it however you want. I mean, you can fix it by saying, I don't know, the first time that the waveform has this amplitude, I don't know, it reaches this value, or the first peak, the first time that the first derivative goes to 0, or it's conventional, I think.
Okay, because
in fact, also, I mean, also experimentally, like I mean, the detector waits for a signal to arrive, but doesn't know. Tomorrow at 4 p.m. At 4:30, we will see a gravitational wave signal. Let's prepare for that. You just have to wait, and then you filter the data, etc., etc. So even I would say that it's even not observable, really. I mean,
yeah, but like we're using this to compare with the post-Newtonian later, right? So like it's the statement that two people agree that at 4.
Yeah, sure. Good point. Thanks. In fact, even in the post-Newtonian thing, it's not observable. And the reason
on
is
time that they're observing it. That's your statement. Like that convention is the same for both.
Exactly. So that corresponds to adjusting this, as you can see also in the post-Newtonian framework, they have this mu IR, which is a scale which is arbitrary, and it's precisely the arbitrariness in the origin of the retarded time. In fact, this is kind of clear from, sorry, I'm going back and forth. This is kind of clear from here, right? So 1 over epsilon carries, brings about this log, this running log, or this arbitrary scale, and changing the origin of retarded time means changing changing the waveform by a constant, I mean an arbitrary constant times I omega times the tree level, which is precisely what you have here. So adjusting this mu corresponds to changing the origin of retarded time. And it's the same ambiguity that they also have in the post-Newtonian calculation. There, instead of, since usually they don't work in dim reg, I think there it arises because of a change of coordinates that you have to do, you know, when you go from this tortoise coordinates to the asymptotic one in precisely in d equal 4, when gravitational interactions are log range, etc., you have a log, and there is a constant in this log that you cannot fix, right? Right, if it's the calculation that you do also when you discuss Schwarzschild in tortoise coordinates that you solve for, you define this R star, and this is this in d equal 5 or 6, this would be a power law. And so you could fix it by saying, it should go to 0. This power law should go to 0 at infinity. You can fix the constant. But in d equal 4, it becomes a log. So you have no preferred way of saying, it should go to 0 at r equal to, I don't know, 1/2. So that's the same ambiguity that you have here.
Okay. And I have one final question, which is that after the first part of the talk, we went, so there it's a function of omega-1 and omega-2, and these define these P's and Q's. And then the second part of your talk, the soft and T, they just have one omega. So like, are you just...
Yeah, sorry, I should have said that more clearly. I think it was written somewhere at some point, but then I didn't emphasize it.
So like, this is just like some effective description for the previous one, where you're just considering a soft expansion to subleading orders and then considering what happens, or... okay.
Yeah, so exactly. So omega is defined in general in this way. It's just the frequency of the graviton as seen from the center of mass frame.
Okay.
So omega-1 and omega-2 are the frequency of the graviton as seen from the rest frame of particle 1 or from the rest frame of particle 2. Then you can define this, which is another frame, the center of mass frame. So this is the general definition. So you can always express the waveform in terms of omega, V1, V2, and possibly another combination, which, I don't know, the antisymmetric combination, P1 minus P2.k if you really want. Then, as you were saying, in the remaining part of the talk, I was focusing on limits. So this soft limit, what we expand is for omega being much smaller than 1 over b. So that's why, I mean, it's convenient to define this alpha 1 and alpha 2 by rescaling omega 1 and omega 2 by omega. But there are still two variables, alpha 1 and alpha 2, which are in principle distinct because the two velocities of the two particles are not assumed to be close to each other. They can be, so these are relativistic invariant expressions if you want. Instead, in the last one, indeed, since, okay, I didn't show the explicit expression, but since we are taking P infinity going to 0, it means that to leading order, omega 1 is equal to omega 2 is equal to omega, because the velocities are tending both to 0, essentially. But to subleading orders, you have differences between omega 1 and omega 2, which have to do with the direction of the graviton. So in particular, this n that I was using is the direction of the graviton or the direction of observation to leading order. They are the same. And so essentially there are differences, but they get expanded out in the PN series.
So why are they the same in the PN case? I didn't quite, like, for the soft case, I kind of understand, but for PN, why would the orientation be the same for the two?
No. It's not that the orientation becomes the same. So let me go back to maybe with the formula, it's a bit easier. So basically in the PN, so okay, in the soft case, I'm just rescaling out omega in this way. But alpha 1 and alpha 2 are completely different in general because I'm not doing any expansion of any kind on the velocities. So they are still independent. In the PN case, what happens is that to leading order, if you want, let me multiply by M1 and M2. To leading order, you get so the spatial part becomes subleading, right? Because it has a power of the velocity, the spatial velocity. Instead, the time part would have the gamma factor of particle 1 or the gamma factor of particle 2, right? But since we are expanding, the gamma factor to leading order is 1, both for particle 1 and for particle 2, right? So the very leading order is just omega for both of them.
Okay.
But then there is, then the first subleading correction knows about the velocity of particle 1 and the velocity of particle 2, which are small. So that's why I was saying they get expanded out. I don't know if that's clearer.
It makes it clear. Thanks. And I forgot there was one final one. Sorry. So you mentioned that region 1 and region 2, right, later on. So are they related to your to this radiation and the Coulombic contributions?
No. I mean, it's a similar mechanism because it's again a method of region thing, but no, they are different from the region versus potential, radiation versus potential. So that, in fact, the method of region is very useful. So you apply it in several different contexts. So the first context, I think this is one you have in mind, is the one in which you have an amplitude, an integrand for an amplitude, and you say, aha, but I'm interested in the small q limit. So then it's convenient to take the small q limit before doing the loop integral. So then, for instance, in this loop here, I have an L, which runs in the loop, and I should discuss different regions. Is L of the same order as Q and both much smaller compared to the masses, say, or is L of the same order of the masses and therefore much bigger compared to Q? These are the say soft versus hard regions in the calculation of the amplitude itself. So all these calculations were done in the soft regions because that's the only one that gives you non-analytic contributions in Q squared, Q1 and Q2 squared. On the other hand, here, probably I should have written down the integral at least once. I have it in the backup slides, but so basically what we are doing here is this Fourier transform, the inelastic one in particular. So in the soft limit, we are saying that omega is going to 0 with respect to B, particular to B1, B2, whatever. So so then we should, and maybe it's even better to look here. So then we should say what Q does, right? Because Q is integrated. So if you're sending omega to 0, we should say whether Q is big or small compared to omega, essentially. And those are the two regions that I was mentioning here. So so these are regions in the Fourier integral that you have to do at the end of the day, not in the loop integral that you have to do in order to get the Q space expression.
The concept that I'm okay, yeah. So it's I got it. It's not got a physical interpretation, but it's the same technical advantage of method of regions.
No, exactly. So technically it's the same. Physically, it actually does, I think. In a sense, this first region, it's the one that gives you the universal pieces because it gives you as you can see, the non-analytic things in B.
Yes.
Because omega you expand it out from the expression because it's small, both compared to Q and respect to B, 1 over B. And then you can only have things that are non-analytic in B. So all these soft theorems all come from, the contributions that match these universal soft theorems for the 1 over omega, for the log omega, can be all deduced from this region only. Yes. And in a sense, you see that's kind of reasonable because this only cares about the really long-range part of your amplitude. This other one, in a sense, cares about the short range, right? Because Q is very small, even compared to 1 over B. So it gives things that are analytic in B, but they are non-analytic in omega. So as long as you have something which is finite, you know that the non-analytic pieces in omega and B must come from log of omega B, essentially. So you can just focus on either of the two. The only problem, the only reason why you would want to calculate this other thing is when you have something that is analytic in omega, and which is not fixed, therefore, by soft theorems. for instance, this beast here, which is rather ugly, it comes from this other region and is not fixed by any soft theorem whatsoever. So in a sense, maybe one could call them the infrared and the ultraviolet regions, or the, I don't know, the long range and the short range regions, something like that, to be a bit more physical.
So the second region is not just coming from, because I recall region 1 is your typical eikonal regime that you would deal with, where you're talking about small exchanges, so you deal with only the non-analytic contributions that you're interested in. And so it's not just an expansion. Region 2 is not just an expansion of this to capture the leading analytic pieces. It's something else. You're going to you're going to a different regime altogether and building up the series from there.
No. Okay, sorry. So Q. So let me phrase it a bit differently. The first step, when you have an integrand, which is in principle valid also at the quantum level for short-range physics, is that you expand for Q very small compared to the masses. So if you want, there is another scale that I'm not drawing here, that in which you expand for omega, generically of the same order as Q, generically of the same order as 1 over B, and all of them much smaller compared to the masses, or of the energy, if you want. So this is what defines the soft region in the sense of the eikonal region or whatever at the level of the integrand. That has been done. So all the masses have been expanded out, all the energies have been expanded out. Now, within these three parameters, what we want to do is to say that omega is much smaller compared to 1 over B. Mm-hmm. And that's what we mean by soft, right? It's the wavelength of these gravitons should be much bigger than B, roughly. Now, since we have three scales still in the game, we have to decide. One is on the left hand, one is on the right hand, the other, where do we put it? So that's what's happening here. Now, within the contributions that are all non-analytic in, let's say, in Q to begin with, you can either generate things that are after integrating in the Fourier transform, you can either generate things that are non-analytic in B, and these are the first region, or that are non-analytic in omega. This is the second region. That's
okay. Now I get it. Okay. Thank you so much. Yeah. I mean, this was very helpful. Very informative.
Okay, great.
Are there any other questions? I think several people have left. So yeah, and I forgot to mention. There are some people who couldn't attend, so I had mentioned that I'd record the talk. So I should have asked.
Yeah, no, I saw it from the program. Yeah, absolutely, no problem.
Yeah, sorry, I should have mentioned that at the beginning. Okay, so are there any other questions? Okay, if not, then let's thank Carlo again. I guess we can do one of these reactions on Zoom.
Yeah.
we give claps.
Thank you.
So yeah, thank you so much again, and yeah, hope to see
you very much.
Thanks
again, and keep in touch.
Sure. Okay, thank you, Carl.
Bye.
Bye.
Bye.